Okay, let's talk about Newton's laws for rotations. Newton's laws for rotations are very much like Newton's laws that you've done before, but now we're talking about extended objects, objects that can rotate, like yourself, like all your body parts. Okay, the analysis can be complicated because there are going to be a lot of pieces to the puzzle, but the basic framework is just like what you've been doing. Namely, Newton's laws for rotation are the net torque on some object. That is, you add up the torque on that object from each individual force. We'll see what that means as we go. That will cause a rotational acceleration if it's unbalanced, and it will have no rotational acceleration or angular acceleration if it is balanced, if it adds to zero. What resists the angular acceleration is the rotational inertia, also called moment of inertia. So that's a property of the object. This is what the object does, and this is what's making it all happen. So as you've been learning, the key principle, perhaps most fundamental principle in physics, is that net interactions cause change or no change if it's in equilibrium. Okay? So keep that in mind. That's what we're looking at. So we pick an object, see what the interactions are, and then we'll analyze it in this way. The term twist is often used, sometimes loosely. It can be used as a cause, which we'll call the torque. So you can say, I take a jar and I cause it, I twist it, I cause the lid to turn. We often use the letter tau, Greek letter tau, which is a curly thing right there, right? Or the word twist can be the effect. It's what happens. It twists. It rotates around some point. Okay? So twist can be a cause or effect. If you want, you can think of torque as the cause, right, of that. So it requires a force, but it requires a force directed around, not through a point. So the effect would be rotation around a point. And that point, you hear a lot of terminology, let's get that straight. It could be called the origin, the pivot point, a hinge, a fulcrum, or an axis of rotation. And with examples, you get used to that. So let's take a look at some examples of that. So the physical pivot point, something that's actually pivoting. If you have something teetering, like a rod here teetering on something as a balance, then we often call that the fulcrum. Okay? And the point where we analyze it would be right there. Okay? And a rod that's attached, here's a wall. We do surfaces often like this in science and engineering. Right? Maybe there's a string holding it up, and maybe there's a sign hanging down from this beam here. And this is often used as a pinned hinge. So there's a pin going through there. And it could rotate. If you cut that string, it's going to fall and rotate around there. So it's still called a hinge, even though you don't want it to rotate. It allows for flexibility. Doors have hinges too. Doors or gates have hinges, and we'll do that problem as an interesting problem to do as well. Here's the wall. Here are the hinges. Now in reality, there's usually 2 or 3 screws at each hinge, so you can look at all that. But we'll just take them as points for our analysis starting out. As you go on in engineering courses, you have a statics course, and then you have a dynamics course, often adding up forces and torques in clever ways, but this is always the foundation. A platform can rotate around. And so if it's rotating, we call this the axis of rotation, like the axle of a wheel. Okay, axis of rotation, rotating one way or the other way. Or here's a wheel, and there's the axle would be coming in and out there like this. And that point would be our axis of rotation, or the origin that we might use to analyze this rotation. So axis of rotation, a line perpendicular to that so-called pivot point. But also, again, we may have this in equilibrium. So there may not be any acceleration. In fact, there might not be any motion. Let's talk about motion over here now. Okay, this is all a bit of a review, which is nice. It doesn't have to be so overwhelming. So rotationally, an object can be in static equilibrium. And rotationally, that would mean that omega, the angular velocity, is 0. And equilibrium means that alpha is 0, and the reason for that is that all the torques, or twists, if you want, add up to 0. They balance. So equilibrium, of course, is in balance. There can also, of course, be dynamic equilibrium, where omega is not 0, it is rotating. Still in equilibrium, so again, alpha is 0, and in that case, then omega would be a constant non-zero value, and it would just keep on going forever. This here is effectively Newton's first law, right? Equilibrium, the law of equilibrium, where things will just keep on spinning forever, never slowing down, never speeding up, and never turning the axis of rotation either. Okay, so there's Newton's first law of for rotations. N1. However, we might have Newton's second law, that is, it does accelerate rotationally. So then you have non-equilibrium or non-balance. And then alpha is not 0, and you could have a couple of cases there. One is you have a constant alpha, and then you can use your constant acceleration equations in terms of the rotational kinematics, which you know how to derive. Or you can have a changing alpha. And then whenever the acceleration is changing, you've got to go back to the basic definitions. So rotationally, that would be alpha is defined as the rate of change of the angular velocity. Angular acceleration, rate of change of angular velocity. Angular velocity, rate of change of angular position. Right? And so you just then take whatever you've got. We won't do this so much because we run out of time, it gets a little overwhelming. But you can get the idea, and it's a nice review of the old stuff as you approach the final and pull it all together. So these are our cases. One law, really, two cases of that law, equilibrium, non-equilibrium. If we have complete static equilibrium, like a bridge, a building, hopefully, even though there's a little wobble there, in that case, we can look at the cause, we can look at the effect. You know what it is. So the effect is that the acceleration is 0. It's static, so we're letting it just sit there. This is a very common and useful case. However, if you're a mechanical engineer, you've got moving parts, right? So you've got moving parts in there too. But this is a good thing to study, and we do a lot of these. So what we need is the net force is 0. Now force is a vector here. Okay, force is a vector. So that means you can't really do this. You've got to break it into parts, x and y parts, and you'll need coordinates. We'll talk about that in a moment. So that means that all the forces have x components, and the sum of the x components of all the forces add to 0, and that, of course, will give you an acceleration of 0 in the x direction. Similarly, in the y direction, but what direction is x and y? Hold on, we'll get to that. Okay, so that's all. So you write that, you look at your picture, and you just start piecing together the puzzle and seeing what you've got. Rotationally, however, you've got torque. You've got some twist that's caused by each of these forces. And so then the net torque is 0, which results in an angular acceleration of 0. Okay, so this has got to be true if we have static equilibrium for any choice. All choices of x, y coordinates, so you could do your x and y however you want. If you got 3 dimensions, you got x, y, and z. That's true. So you're free, but let's use good choices. Let's use wise choices. This has to be true for all choices of origin or pivot point or axis of rotation, whatever you want to call it. Okay, so that's got to be true. The key is that wise choices, as you've hopefully seen and remember, wise choices will make the mathematical analysis easier and likely make the conceptual understanding, it'll be a little clearer to you if you think in terms of good x and y coordinates for this, and taking the same forces and now looking at the twist around some point, even though it's not even twisting. So we'll take a look at that. Okay. And it won't matter because they're all got to add up to 0 in this case. All right, so to finish this off here, let's go over here. And let's talk about extended objects. So now things are not a point. We don't take them as a point like we did earlier in the course. And we've got second law, and it's the first law when in equilibrium, so it's effectively the same law, just two cases of the same law. And we've got rotational and translational. what we've already written, but a little more detailed here, just to lay the groundwork, right? Just to think about this, and then you can move on and actually apply it where it all comes together. I put rotational before translation for one very practical reason. As a student, you got to get your homework done quickly. You got to get the exam problems quickly. You got to get to the heart of a problem. Since this is new material, a lot of problems, you just need this. My recommendation is start with torque, unless it's obvious otherwise. But if you're not sure, start here. Start with the new, because sometimes you've got enough information and that's going to solve your problem. A lot of problems, though, will require you to do the translational, which is moving side to side, in the x, and perhaps the y, or maybe just the y, right? Don't put in an x component if you don't. If all things are vertical, all forces are vertical, don't do that. That's a waste of time. But again, keep in mind that just as the forces are from other objects, which I call sources, or some people call agents, on that particular object you're looking at, that extended object, these are the interactions. They cause it to change, the motion. Right? And this is the resistance to change, the inertia. But we're breaking it into x and y parts, because it's 2D or 3D if you had it, but we won't do that so much. Similarly, these torques are from interactions. They're from the same forces. So their torques are from anything touching your rod or ladder or beam. But we have to select an axis, just like over here, we have to select x and y coordinates. We have to select an axis of rotation, a pivot point, to do the calculation for calculational purposes, right? Okay. Now, let me just say that the choice of coordinates here, usually when we're talking about beams, ladders, bridges, vertical and horizontal, y and x, is usually what we use in practical cases. There might be cases where you do other things. Molecularly, you might not care about vertical, horizontal, but in terms of structurally, you might. So that's often the standard choice, unlike when we had things sliding up and down inclined planes, ramps. Okay. And this we'll talk about. So what's your method? The method is same old thing, good news. So you think it's new, and sometimes your brain short circuits, but you realize, hey, wait a minute, I just have to choose my object, but now my object might be a rod, some sort of thing like this, some object here, or a beam that's holding a sign or holding something up, a ladder propped up against a wall, right? That's good. Rotating discs, things that are spinning around. Solid discs, rings. If you take a look at this object here, can you see it? There's a motor, things are spinning, rotating. I got this disc rotating, I got this disc rotating, I got gears rotating, I got things rotating, right? So from a mechanical engineering point, you might want to design things with the mathematical analysis, but you also need an intuition and make a prototype and see if it falls apart or works. So we couple the intuition, the prototype, the physical making, manufacturing of the thing, with the mathematical analysis, and that can lead to some really cool stuff. So you choose your object, just like before, but now it's an extended object. You identify all objects interacting with it, all the sources. So what's touching it? And gravity right now. Right? If you got electric force later, or magnetic force, you can deal with that just the same old way. But now we're just looking for things touching it and gravity. Then you do the same old free body diagram. So to do torques and forces, it's just the same free body diagram. So that's like, oh, really? Yeah, just that. But you do care about where the force is applied, because it is an extended object. And so that's key. Okay? So you have to draw the extended object and see where the force is applied. So that's the free body diagram as usual. Those forces are the ones that create those torques, the causality of twisting, or the twisting force.
Excuse me, I have to stop this. This is an emergency. There's a gas leak. I need a home to evacuate, please.
Okay,
Sorry about that.
we're gonna evacuate and come back later.